Welcome you all. In this video, we are going to see about Introduction to VLSI. What is VLSI? VLSI abbreviate Very Large Scale Integration. In here, we integrate million number of transistors on a single chip. So it is named as VLSI. When we are integrate million number of transistors on a single chip, the design engineer mainly focusing three parameters, that is size of the IC, size of the speed of the chip, power of the chip or IC. In 1965, Morse defined about transistor counts on a single chip. He stated that the number of transistors on a chip doubled every 18 to 24 months. This graph shows the concept of Moore's law. That is, every 18 to 24 months, the transistor counts will be doubled on a single chip. We are following different generation of IC. In 1960, we followed small scale integration. It has 10 power 2 transistor count. In 1967, we followed medium scale integration generation IC. Here, transistor count from 10 power 2 to 10 power 3. Then we moved to next generation IC. In 1972, we followed large scale integration. Here transistor count from 10 power 3 to 10 power 5. Then we entered into VLSI in 1978. That is here transistor count from 10 power 5 to 10 power 7. After that, we moved to 1989 ULSI. In 2000, Giant scale integration generation of IC. Anyway, VLSI is a famous familiar name, so only we are telling VLSI design logic. What kind of technology followed in IC in VLSI? Mainly, we are following lot of technology for integrated circuit. In VLSI, CMOS technology is dominant because silicon is cheaper preferred over other material. CMOS means complementary metal oxide, that is easier to implement or fabricate. It provides low power delay product. It can get more CMOS transistor or functions in same chip area. So only we prefer CMOS technology. This is the general design flow of VLSI, which means from specification to silicon. Design flow means design process of IC and developing the IC. Here we have followed lot of steps to design an IC. The very first step is named as system specification. After the system specification, we move to the architectural design. Then after the design, move to the functional and logical design. After that, we enter into circuit design. Then next we move to the physical design. The physical design includes lot of steps, that is partitioning, planning, placement, clock tree synthesis, signal routing, timing, closure. So after that, we move to the physical verification and sign off. Once we check the sign off everything, we move to the layout post processing, then move to the fabrication unit, then finally packaging the IC and testing the IC. These are the steps followed in design flow of VLSI. Let us discuss one by one. Very first step is system specification. Based on the customer need, we describe the specification of our chip. Here we define the chip's purpose and requirements. It includes performance, power, area and cost target. So here not defined about implementation. At this stage only we defined about what the chip should achieve. Okay. Then we move to the architectural design. Here selects what are the system architecture to be followed in our IC design or chip design. For example, what are the processor we are going to use, that is RISC or DSP. What kind of determines what kind of block level optimization we are going to follow, that is CPU, memory unit, IO port and then interconnects. Then Here balance the trade-off between performance, area, and power consumption. Then after that, produce high-level design documents and block diagram. In architectural design, we only produce high-level design documents and block diagram. Then after that, we move to the functional and logic design. In functional design means here describes the circuit's behavior using hardware description language. Hope everyone know the hardware description language. Here we know the concept of VHDL and Verilog. Either VHDL or Verilog, we are describes the circuit behavior of the design. Once we design a written a code, then we performs initial simulation to verify logic. After that, we move to the logic design. Here, our written code is converted into port netlist, that is function to maps function to logic gates and flip flops. Here we ensures the correct Boolean implementation and timing estimates. After that, we move to the circuit design. Here we design logic gates at the transistor level. Before that, we followed here logic gates level. Here we are converted into transistor level. Once converted to transistor level, we optimize for delay, noise margin, and power consumption. It determines, here we determines transistor sizing for required performance. We also prepare the for conversion to physical layer. Once we everything done, we move to next step is physical design. So physical this is the major part of the design. Here converts circuit description to actual silicon layout. It includes several steps. Steps are partitioning, floor planning, placement, clock tree synthesis, signal, routing, and timing closure. Let's discuss one by one. Partitioning and floor planning. Partitioning means, which means we divides design into sub blocks. There is manageable sub blocks. After that partitioning, we move to the floor planning. Here we decide the placement of blocks to minimize wire length and delay. Once ensured heat distribution and power routing feasibility. After that partitioning and floor planning, we move to the placement, CTS and routing. Placement means position standard cells within blocks optimally. Optimally we place the standard cells within blocks. This is named as a placement. Once placed our cells, we follow the clock tree synthesis concept. Here we distribute the clock signal uniformly to avoid skew. Okay. So after the distribution of clock signal, we connects all placed cells and blocks using metal interconnects. It is named as signal routing. Once we completed routing, next we check the timing closure. That is move to the timing closure part. But that means here ensure all signal paths meet timing constraints or not. Once we that means here we fixes the setup time, hold and clock skew violation. It may require buffer insertion. Suppose we require means if include buffer insertion, resizing or rerouting. Once everything completed, next we move to the physical verification and sign off. Here we checking the DRC, LVS and ERC. DRC means design rule check. Here ensures layout follows foundry rules. LVS means layout versus schematic. Here verifies the layout matches our original schematic, that is our circuit. So before the first we designed a Verilog code. Verilog code is converted into circuit diagram. One circuit diagram converted into layout form. Once we convert in the layout form, again we can verify the functionality layout with our original schematic. That is named as a LVS. After that we followed electrical rule check. Here we validate electrical connectivity and power limits. So sign off ensures the design is ready for fabrication. Once we verify the everything, that is the sign off ensures the design is ready for fabrication. Then after that, enter into layout post processing. Here we add the dummy fill pattern for uniform density final adjustment for manufacturing compliance, and also prepare GDS2 or OSIS file for tape out. Tape out means we send to the our design file GDS2 file to fabrication unit. Here, fabrication design engineers verify designs into semiconductor foundry. Here, here we perform the wafer processing. Wafer processing already we know lithography, etching, doping, level metal deposition. Here produce a bar silicon dies ready for packaging. Our design die is ready here. Okay, that is the which means produce bar silicon dies ready for packaging. Once ready our design at wafer level, we move to the packaging and testing part. Here our die in a protective package with external pins or bumps. Electrical and functional testing ensures quality. Then finally product is ready for deployment. This is the final step for our IC. So in VLSI design flow, each stage is critical for achieving high performance and yield. So this is the overall chip design concept in pictorial representation. There is specification to silicon. Same concept here repeated in pictorial representation. Our idea convert to spec convert to written Verilog code or VHDL, HDL code. HDL code convert to synthesis part. Synthesis convert to the circuit convert to physical design. Then sign off check. Then convert to wafer part. When our die is ready, our packaging and final testing, and convert into board level design, finally comes as a product. This is the chip design concept. Here we verify the we follow the pre-silicon validation and post-silicon validation. Once our die in packaging level, we verify the silicon validation, follow the post-silicon concept. Before in our RTL design level, we verify the logic, that is a pre-silicon validation, that is DFT. Here one more major part is we followed DFT, design for test.